Imagine waking up one morning, ready to face your day, maybe sipping on coffee, only to discover the sun is gone, replaced by a silent, invisible monster in the sky. No sunrise, no warm rays on your skin, just a chilling darkness where our life-giving star used to be, and a gravitational mystery that could tear the fabric of reality apart. What would happen to our planet, to us, if the sun instantly became a black hole? Stay tuned, curious minds, as we unravel this cosmic catastrophe and reveal truths that will boggle your imagination. If space mysteries and scientific wonders keep you up at night, make sure to subscribe to the Sleepy Cosmoz for more journeys through the dark and dazzling corners of our universe. Our sun is an absolutely magnificent cosmic powerhouse that defies human comprehension, a blazing sphere of plasma so massive that it contains 99.86% of all the matter in our entire solar system. To truly grasp the scale we're dealing with, imagine trying to fit 1.3 million Earths inside this stellar giant. That's the sheer volume we're talking about. The sun's mass is so overwhelming that it's 333,000 times heavier than our entire planet, creating a gravitational field so powerful that it holds 8 planets, countless asteroids, comets, and debris in perfect orbital harmony across billions of miles of space. Every single second of every single day, this cosmic furnace is performing nuclear alchemy on a scale that would make ancient alchemists weep with envy, converting an astounding 600 million tons of hydrogen into helium through the process of nuclear fusion. This isn't just any ordinary energy release. We're talking about the equivalent of 100 billion hydrogen bombs exploding simultaneously, every second, for the past 4.6 billion years without stopping even once. Deep within the sun's core, conditions exist that are so extreme they border on the impossible. Temperatures soar to an incomprehensible 27 million degrees Fahrenheit, hot enough to instantly vaporize any known material and strip electrons from atoms, creating a soup of charged particles called plasma. The pressure at the sun's center is equally mind-boggling, 250 billion times greater than Earth's atmospheric pressure at sea level, which means that if you could somehow transport a single cubic inch of the sun's core material to Earth, it would weigh about 250 pounds. Under these unimaginable conditions, hydrogen nuclei are smashed together with such violent force that they overcome their natural electromagnetic repulsion and fuse into helium, releasing tremendous amounts of energy in the process. This energy doesn't just appear instantly at the sun's surface. It begins an epic journey that can take anywhere from 10,000 to 170,000 years to travel from the core to the surface, bouncing around like a pinball through the dense solar material, getting absorbed and re-emitted countless times before finally escaping into space as the sunlight that warms your face. What makes our sun truly remarkable is the delicate cosmic balance it maintains every moment of its existence, a perfect equilibrium between two titanic forces that are locked in an eternal struggle. Gravity, that fundamental force that shapes the universe, is constantly trying to crush the sun inward, attempting to compress all of its mass into the smallest possible space. If gravity had its way, our sun would collapse into a point smaller than a marble in less than 30 minutes. But standing against this crushing gravitational force is the outward pressure generated by nuclear fusion reactions, creating a constant expansion pressure that pushes against gravity's inward pull. This balance is so precise that if the fusion rate increased by just a small percentage, the sun would expand dramatically, potentially becoming a red giant and engulfing the inner planets. Conversely, if the fusion rate decreased even slightly, gravity would begin winning the battle, causing the sun to contract and heat up until fusion rates increased again. The sun's structure is like a perfectly engineered cosmic machine with distinct layers, each serving a crucial purpose in maintaining this stellar balance. At the very center lies the core, extending about 20 to 25% of the sun's radius, where all the nuclear fusion occurs and temperatures remain consistently above 10 million degrees Celsius. Surrounding the core is the radiative zone, where energy produced in the core slowly makes its way outward through a process of absorption and re-emission, with photons taking their sweet time, sometimes tens of thousands of years, to travel through this dense region. Above the radiative zone sits the convective zone, where hot plasma rises toward the surface while cooler material sinks back down, creating massive circulation patterns that transport energy upward much more efficiently than the radiative process below. Finally, we reach the photosphere, the sun's visible surface, where temperatures drop to a relatively cool 5,778 Kelvin, and where sunlight finally escapes into space after its incredibly long journey from the core. But here's where things get absolutely fascinating. The sun isn't just a static ball of fire sitting motionless in space. It's a dynamic, ever-changing system with an incredibly powerful magnetic field that's about twice as strong as Earth's magnetic field, twisted and stretched by the sun's rotation and convective motions. This magnetic field creates the spectacular phenomena we observe, including solar flares that can release the energy equivalent of billions of nuclear bombs, and coronal mass ejections that hurl billions of tons of charged particles into space at speeds exceeding 1,000,000 miles per hour. The sun rotates on its axis, but not like a solid object. Different parts of the sun rotate at different speeds, with the equator completing one rotation every 25 days, while the poles take about 35 days, creating a differential rotation that continuously twists and tangles the magnetic field lines. Every 11 years, the sun goes through a complete magnetic reversal during what we call the solar cycle, where the magnetic north and south poles literally flip positions, causing dramatic changes in solar activity and the number of sunspots visible on the surface. These sunspots, which appear as dark patches on the sun's surface, are actually regions where intense magnetic fields have broken through the photosphere, temporarily cooling those areas by several thousand degrees and creating what appear to be dark spots against the brighter surrounding material. During solar maximum, when the magnetic field is most tangled and complex, we can see dozens of sunspots and experience increased solar flares and geomagnetic storms that can affect satellite communications and power grids here on Earth. The energy output of our sun is so consistent and reliable that we've built our entire understanding of stellar physics around it. And this consistency is absolutely crucial for life on Earth. The sun radiates energy at a rate of 3.8 times 10 to the 26th watts, which means it produces more energy in 1 second than humanity has consumed in our entire history. This energy travels the 93 million miles to Earth in just 8 minutes and 20 seconds, arriving as the electromagnetic radiation we call sunlight, which includes not just visible light, but also ultraviolet radiation, infrared heat, and small amounts of X-rays and radio waves. The amount of solar energy that strikes Earth's atmosphere every hour is greater than all the energy humanity consumes in an entire year, highlighting just how incredibly powerful our neighborhood star really is. What's truly mind-blowing is that the Sun has been maintaining this incredible output for 4.6 billion years and will continue to do so for another 5 billion years before it begins to run out of hydrogen fuel in its core. When that happens, the delicate balance between gravity and fusion pressure will begin to shift, causing the Sun to expand into a red giant star that could potentially engulf Mercury, Venus, and possibly even Earth. But for now, in this cosmic moment, our Sun represents the perfect stellar middle age, stable, consistent, and absolutely essential for every form of life we know. The Sun's gravitational influence extends far beyond the visible planets, creating what we call the heliosphere, a vast bubble in space where the solar wind dominates over interstellar medium, stretching more than 100 times the distance from Earth to the Sun. This is the cosmic stage we're about to transform in our thought experiment, where we'll replace this magnificent, life-giving star with something far more sinister and mysterious, a gravitational monster that consumes light itself and warps the very fabric of space and time around it. Black holes represent the most extreme and terrifying objects in the entire universe, cosmic monsters so fundamentally alien to our everyday experience that they challenge everything we think we know about reality itself. These aren't just empty holes in space, as their name might suggest. They're regions where matter has become so incredibly dense that they've literally broken the fabric of space-time, creating gravitational fields so powerful that nothing, absolutely nothing, can escape once it crosses a certain boundary. To understand what we're dealing with, imagine taking all the mass of our Sun and compressing it down to a point smaller than the tip of a needle. That's the kind of density we're talking about when we discuss the singularity at a black hole's center, where the laws of physics, as we know them, completely break down and cease to make any logical sense. The story of how black holes form in nature is both fascinating and terrifying, beginning with stars that are at least 20 to 25 times more massive than our Sun. These stellar giants live fast and die young, burning through their nuclear fuel at an incredible rate, because their immense mass creates such extreme pressures and temperatures in their cores that fusion reactions proceed at breakneck speed. When these massive stars finally exhaust their nuclear fuel, the delicate balance between outward radiation pressure and inward gravitational pull that we discussed with our Sun suddenly collapses in the most violent way imaginable. Without fusion reactions to provide the outward pressure needed to support the star's enormous mass, gravity wins decisively, causing the entire star to collapse in on itself in less than 1 second. This collapse is so rapid and violent that the star's core, which might be the size of Earth, gets compressed to a point just a few miles across, while the outer layers explode outward in what we call a supernova, an explosion so bright it can outshine an entire galaxy containing billions of stars. But here's where things get truly mind-bending. The core doesn't just stop collapsing when it reaches some incredibly dense state. It continues collapsing until it becomes what physicists call a gravitational singularity, a point of theoretically infinite density where space and time themselves become infinitely curved. Around this singularity lies the most famous and terrifying feature of any black hole: the event horizon, an invisible boundary in space beyond which escape becomes absolutely impossible. The event horizon isn't a physical surface you could touch or see. It's more like a one-way membrane in space-time itself, marking the point where the escape velocity needed to get away from the black hole exceeds the speed of light. Since nothing in the universe can travel faster than light, anything that crosses the event horizon is doomed to spiral inward toward the singularity, never to return to the outside universe again. The size of a black hole's event horizon depends directly on its mass, following a surprisingly simple relationship that demonstrates the elegant mathematical beauty underlying these cosmic monsters. For every solar mass of material that falls into a black hole, the event horizon's radius increases by about 3 kilometers, creating what scientists call the Schwarzschild radius. This means that if our sun were somehow compressed into a black hole, which, remember, is physically impossible given the sun's mass, the resulting event horizon would have a radius of approximately 3 kilometers, creating a sphere about 6 kilometers across, where our massive star once blazed. To put this in perspective, you could fit this entire black hole inside most major cities, yet it would contain all the mass that currently makes up our 1.4 million kilometer diameter sun, representing a compression factor that's almost impossible to comprehend. What makes black holes even more terrifying is how they interact with space-time itself, literally warping the fabric of reality around them in ways that would make science fiction writers jealous. According to Einstein's theory of general relativity, massive objects don't just attract other objects through some mysterious force. They actually bend and curve the four-dimensional fabric of space-time, and objects follow the straightest possible paths through this curved geometry. Near a black hole, space-time becomes so severely warped that what we perceive as straight lines curve dramatically inward toward the singularity. This warping effect becomes so extreme near the event horizon that time itself begins to behave in ways that seem impossible from our everyday perspective. If you could somehow observe someone falling into a black hole from a safe distance, you would see something absolutely bizarre. As they approach the event horizon, they would appear to slow down dramatically due to gravitational time dilation, their movements becoming slower and slower until they seem to freeze completely at the event horizon boundary, their image growing redder and dimmer until it faded from view entirely. But from the perspective of the person falling into the black hole, their experience would be completely different and far more terrifying. They wouldn't notice any slowing of time. Their watch would tick normally, and they would cross the event horizon in a finite amount of time from their perspective. However, they would encounter something far worse: tidal forces that would literally stretch their body apart in a process that scientists have dubbed spaghettification. These tidal forces occur because the gravitational field becomes so strong and varies so dramatically over short distances that the difference in gravitational pull between your head and feet would become overwhelming. The part of your body closer to the black hole would experience significantly stronger gravitational attraction than the parts farther away, stretching you vertically while simultaneously compressing you horizontally until you resembled a piece of spaghetti. Hence the rather morbid but descriptive name. Black holes also possess another mind-bending property called frame dragging, where the rotation of the black hole literally drags space-time around with it, forcing anything nearby to rotate in the same direction as the black hole itself. This effect creates what's known as the ergosphere, a region outside the event horizon where nothing can remain stationary relative to distant observers. Everything must rotate with the black hole, whether it wants to or not. In supermassive black holes that rotate rapidly, this frame dragging effect can be so powerful that it could theoretically be used to extract energy from the black hole through a complex process involving dropping objects into the ergosphere and retrieving them with more energy than they had initially, effectively stealing rotational energy from the black hole itself. The detection and study of black holes represent some of the most incredible achievements in modern astronomy, accomplished through ingenious, indirect methods, since black holes themselves emit no light. Astronomers identify black holes by observing their gravitational effects on nearby matter, watching as stars orbit invisible companions with masses far too large to be any known type of star, or by detecting the high-energy radiation emitted by matter as it spirals into the black hole and gets heated to millions of degrees in the process. When matter falls toward a black hole, it doesn't fall straight in. Instead, it forms what's called an accretion disk, a swirling, flattened structure of superheated gas and plasma that glows brilliantly in X-rays as friction and magnetic fields heat it to temperatures exceeding 10 million degrees Celsius. Perhaps most remarkably, we've recently been able to actually photograph the shadow of a black hole's event horizon using a planet-sized network of radio telescopes called the Event Horizon Telescope. These images show the distinctive dark shadow of the event horizon surrounded by the bright glow of the accretion disk, providing direct visual confirmation of these theoretical predictions. The first such image, captured in 2019, showed the supermassive black hole at the center of the galaxy M87, which contains the mass of 6.5 billion suns and has an event horizon larger than our entire solar system. The universe contains black holes of vastly different sizes, from stellar mass black holes formed by collapsing stars that might be just a few times more massive than our Sun, to intermediate mass black holes that could contain hundreds or thousands of solar masses, to the supermassive black holes found at the centers of galaxies that can contain millions or billions of times the mass of our Sun. These supermassive black holes play crucial roles in galaxy formation and evolution, regulating star formation through their powerful gravitational influence and the energetic jets they can produce when actively feeding on surrounding matter. What we're about to explore in our thought experiment, transforming our Sun into a black hole, would create something unprecedented in our solar system. We'd be replacing a life-giving, energy-producing star with a light-consuming gravitational monster that operates by completely different physical principles, setting the stage for the most dramatic cosmic catastrophe our planet could possibly face. Now, we enter the realm of pure scientific speculation, where we must temporarily suspend the laws of stellar physics to explore a transformation that nature itself has deemed absolutely impossible. Under normal circumstances, our Sun could never become a black hole because it simply doesn't have enough mass, not even close. The minimum mass required for a star to collapse into a black hole is called the Tolman-Oppenheimer-Volkoff limit, approximately 2.17 times the mass of our Sun. And this isn't just a suggestion from the universe. It's an ironclad rule enforced by the fundamental forces of physics. Stars with less mass than this limit, like our Sun, are destined for far more peaceful endings, eventually swelling into red giants before gently puffing off their outer layers and settling into retirement as white dwarf stars, slowly cooling over trillions of years until they become cold, dark remnants floating through space. But let's imagine, for the sake of our cosmic thought experiment, that some unimaginably powerful force, perhaps an advanced alien civilization with technology beyond our wildest dreams, or some fundamental breakdown in the laws of physics themselves, suddenly compressed our sun's entire mass into a sphere just 6 kilometers in diameter. This transformation would need to happen instantaneously, faster than light could travel across the sun's surface, because if the process took any longer, the outer layers of the sun would have time to react and potentially escape the gravitational collapse. The energy required to accomplish such a feat would be absolutely staggering. We're talking about compressing 2 times 10 to the 30 kilograms of matter from a diameter of 1.4 million kilometers down to just 6 kilometers, overcoming not just the sun's own gravitational binding energy, but also the enormous pressure created by nuclear fusion and the electromagnetic forces holding atomic nuclei apart. The moment this impossible transformation began, the very fabric of space-time around our solar system would start to warp and bend in ways that have never occurred in the 4.6 billion year history of our cosmic neighborhood. Imagine space-time as a stretched rubber sheet, and our current sun as a bowling ball, creating a gentle depression in that sheet. Suddenly, that bowling ball gets replaced by something infinitely denser, not just heavier, but so compact that it punches a hole straight through the rubber sheet itself, creating a funnel-shaped depression so deep and steep that it fundamentally changes the geometry of space in our entire solar system. Gravitational waves, ripples in space-time itself, would radiate outward from this transformation at the speed of light, carrying energy equivalent to the explosion of billions of nuclear weapons and potentially detectable by gravitational wave observatories throughout the galaxy. The physics governing this transformation would involve some of the most extreme conditions possible in our universe, where quantum mechanics and general relativity clash in ways that our current scientific understanding cannot fully describe. As the sun's matter compressed beyond the point where even neutron degeneracy pressure could resist the gravitational collapse, individual protons and neutrons would be crushed together so violently that they would lose their individual identities, potentially forming exotic states of matter that exist nowhere else in the known universe. Quarks, the fundamental building blocks of protons and neutrons, might be liberated from their normal confined states, creating a quark-gluon plasma similar to what existed in the first microseconds after the Big Bang, but under gravitational pressures millions of times more extreme. During the final moments of this compression, as the matter approached the formation of the event horizon, time dilation effects would become so severe that the transformation would appear to happen at different rates depending on where you observed it from. If you were somehow positioned at a safe distance from the sun, you would see the compression slow down dramatically as the matter approached the critical density, appearing to freeze at the moment the event horizon formed, with the last photons of sunlight becoming increasingly redshifted until they faded into infrared radiation and then disappeared entirely. But from the perspective of the matter itself undergoing compression, the transformation would continue at a normal pace, with the formation of the singularity occurring in a finite amount of proper time, even as billions of years might pass for outside observers. The mathematical description of this transformation involves some of the most complex equations in theoretical physics, combining Einstein's field equations of general relativity with quantum field theory in ways that push the boundaries of human mathematical understanding. The metric describing space-time around our newly formed black hole would transition from the relatively simple description of spacetime around a normal star to the much more complex Schwarzschild metric, characterized by coordinate singularities and event horizons that represent fundamental changes in the causal structure of spacetime itself. The curvature of spacetime would become so extreme near the event horizon that tidal forces would vary dramatically over distances as small as a few meters, creating gravitational gradients thousands of times stronger than anything that exists in nature today. As the transformation completed and our new solar black hole settled into its final configuration, it would possess several key characteristics that would make it fundamentally different from any astronomical object our solar system has ever contained. Its event horizon would have a circumference of approximately 18.8 kilometers and an area of about 113 square kilometers, roughly the size of a small city, yet containing the entire mass that once powered life on Earth for billions of years. The gravitational field at the event horizon would be about 153 billion times stronger than Earth's surface gravity, meaning that even photons, particles of pure energy traveling at the maximum possible speed, would be unable to escape once they crossed this boundary. The surface gravity of our solar black hole would create tidal forces so intense that they would be detectable throughout the solar system, causing measurable changes in the orbits of planets and potentially triggering seismic activity on rocky worlds as gravitational stresses flexed and twisted their internal structures. These tidal effects would be particularly pronounced on any moons or asteroids that happen to be in highly elliptical orbits, as they would experience dramatically different gravitational forces at different points in their orbital paths. The gravitational time dilation near the event horizon would be so extreme that a clock placed just outside the event horizon would tick at a rate nearly 71% slower than identical clocks located at Earth's distance from the Sun. Perhaps most remarkably, our solar black hole would possess what physicists call a photon sphere at a radius of 4.5 kilometers from the center, a region where photons can theoretically orbit the black hole indefinitely, neither falling in nor escaping to infinity. This photon sphere represents the closest possible stable circular orbit for any massless particle, and it would serve as a kind of gravitational boundary layer where the physics of light itself would be stretched to its absolute limits. Any photon that ventured closer to the black hole than this radius would inevitably spiral inward toward the event horizon, while photons farther away would either escape to infinity or settle into highly elliptical orbits that would eventually decay due to the emission of gravitational waves. The formation of our solar black hole would also create what's known as a gravitational potential well, so deep and narrow that it would fundamentally alter the energy requirements for any object trying to escape from various distances throughout the solar system. Spacecraft that currently require specific velocities to escape from different planetary orbits would find these escape velocities dramatically increased, particularly for objects in the inner solar system. The gravitational binding energy of our solar system would increase so dramatically that it would effectively become a gravitational prison for any matter not already traveling at near relativistic speeds. During the actual moment of transformation, if such a moment could be precisely defined given the relativistic effects involved, the conservation of angular momentum would require our solar black hole to be rotating at an incredible rate. Since black holes can rotate up to a maximum rate determined by their mass, beyond which they would become naked singularities and violate cosmic censorship. Our solar black hole would likely settle into a state of near maximal rotation, creating powerful, frame-dragging effects that would literally twist space-time in our solar system like cosmic taffy. This rotation would create an ergosphere extending several kilometers beyond the event horizon, where the rotation of space-time itself would be so strong that nothing could remain stationary relative to distant stars. The completion of this impossible transformation would mark the beginning of the most dramatic chapter in the history of our solar system, replacing the warm, life-giving radiation that has sustained Earth's biosphere for billions of years with something far more sinister, a cosmic vacuum cleaner that consumes light itself and offers nothing in return but the cold mathematics of general relativity and the promise that anything venturing too close would be stretched, compressed, and ultimately dissolved into the fundamental quantum foam that underlies the structure of space-time itself. The moment our sun transforms into a black hole, the first and most counterintuitive truth would hit us like a cosmic revelation. Earth would continue orbiting exactly as it always has, at least initially. This might seem impossible given everything we associate with black holes, their reputation as cosmic destroyers that consume everything in their path. But the fundamental laws of physics tell a different story. Gravity depends only on mass and distance, not on the nature of the object creating that gravitational field. Since our hypothetical solar black hole contains exactly the same mass as our original sun, just compressed into an incomprehensibly smaller volume, the gravitational force experienced by Earth at its current orbital distance of 150 million kilometers would remain absolutely identical to what it experiences today. This gravitational consistency represents one of the most elegant aspects of Einstein's theory of general relativity and Newton's law of universal gravitation working in perfect harmony. The mathematical equation F equals gm over r squared doesn't care whether the mass m is distributed across 1.4 million kilometers of glowing plasma or compressed into a 6-kilometer sphere of infinitely dense matter. As long as the total mass remains constant and we're measuring from the same distance, the gravitational force remains unchanged. Earth would continue its elliptical dance around our new cosmic monster at the same average speed of 29.78 kilometers per second, completing one orbit every 365.25 days, maintaining the same perihelion and aphelion distances that have characterized our planet's journey around the Sun for billions of years. However, this gravitational stability would only apply to objects that maintain their current orbital distances. The moment any piece of matter ventures significantly closer to our solar black hole, the story becomes dramatically different and far more terrifying. The gravitational field strength increases with the square of decreasing distance, which means that as objects approach the compressed mass of our former sun, they encounter gravitational forces that become exponentially more powerful than anything they've ever experienced. At a distance of just 1 million kilometers from our solar black hole, still about 167 times farther than the black hole's event horizon, the gravitational acceleration would be over 22,000 times stronger than what the same object would experience at that distance from our normal sun. The tidal forces created by our solar black hole would represent the most dramatic change in our solar system's gravitational environment, introducing effects that would be completely unprecedented in the history of planetary mechanics. Tidal forces occur because gravity weakens with distance, creating a differential pull across the extent of any extended object. While our normal sun creates gentle tidal forces that cause phenomena like ocean tides on Earth, our solar black hole would generate tidal forces millions of times more intense for objects at equivalent distances. These forces would become particularly dangerous for any asteroids, comets, or spacecraft that happen to be on highly elliptical orbits that brought them significantly closer to our transformed star. Consider what would happen to a typical asteroid on an orbit that brought it within 10 million kilometers of our solar black hole. Still, 1,667 times farther than the event horizon. The gravitational force on the side of the asteroid facing the black hole would be significantly stronger than the force on the far side, creating a stretching effect that could literally tear the asteroid apart if it wasn't held together by sufficient internal cohesion. Rock and metal that had remained gravitationally bound for billions of years would suddenly find themselves subjected to differential forces capable of overcoming the electromagnetic forces holding their crystalline structures together, reducing solid asteroids to streams of debris spiraling inward toward the event horizon. The mathematical description of these tidal forces involves calculating the gradient of the gravitational field, which for our solar black hole becomes extraordinarily steep very quickly as distance decreases. The tidal acceleration experienced by an object of length L at distance r from our black hole would be approximately 2 gml over r cubed, where g is the gravitational constant and m is the mass of our solar black hole. This means that tidal forces increase as the cube of decreasing distance, making them far more dangerous than the primary gravitational force itself as objects approach the black hole. An object that could comfortably orbit our normal sun at a distance of 1 million kilometers would be subjected to tidal forces over 2.7 billion times stronger when orbiting our solar black hole at the same distance. The gravitational time dilation effects created by our solar black hole would introduce another layer of complexity to orbital mechanics throughout our solar system, creating scenarios that seem to violate our intuitive understanding of time and causation. Clocks located closer to the black hole would tick more slowly relative to clocks farther away, with this effect becoming more pronounced as distance to the black hole decreases. At Earth's orbital distance, this time dilation would be utterly negligible, less than 1 part in a billion billion. But for any objects that ventured closer to our cosmic monster, time would begin to crawl relative to the rest of the solar system. The gravitational potential well created by our solar black hole would be so much deeper and more concentrated than our current sun that it would fundamentally alter the energy requirements for interplanetary travel throughout our solar system. Spacecraft that currently use gravitational slingshot maneuvers around planets to gain velocity would find these techniques dramatically more effective when performed near our solar black hole, but also exponentially more dangerous. A spacecraft that ventured close enough to our black hole to achieve significant velocity gains would need to navigate gravitational fields billions of times stronger than anything human technology has ever encountered, requiring navigation precision measured in meters rather than kilometers to avoid crossing the point of no return. The conservation of angular momentum would create particularly interesting effects for any matter that began spiraling toward our solar black hole. As objects moved closer to the black hole, they would begin orbiting faster and faster, following Kepler's laws, but in an extremely compressed gravitational field. Matter that started in wide, slow orbits would find itself accelerated to tremendous velocities as it spiraled inward, potentially reaching speeds approaching significant fractions of the speed of light before crossing the event horizon. This acceleration process would convert gravitational potential energy into kinetic energy with perfect efficiency, creating one of the most efficient energy conversion processes possible in the universe. The frame-dragging effects of our rotating solar black hole would introduce rotational components to gravity that have never existed in our solar system, literally twisting the fabric of space-time and forcing nearby objects to rotate in the same direction as the black hole itself. This effect, predicted by Einstein's theory, but never experienced on such a scale in our solar system, would become noticeable for objects within several thousand kilometers of the event horizon, creating orbital precession and rotational coupling that would make navigation near the black hole even more complex and dangerous. Perhaps most remarkably, our solar black hole would create gravitational lensing effects that would be visible throughout the solar system, bending and focusing light rays that passed near the black hole in ways that could theoretically allow observers in the right positions to see multiple distorted images of the same distant objects. The intense gravitational field would act like a cosmic magnifying glass, but one that distorts and multiplies images rather than simply enlarging them. Starlight passing close to our solar black hole would be bent so severely that it could create Einstein rings, perfect circles of light formed when the light source, the black hole, and the observer are perfectly aligned. The gravitational waves produced by matter spiraling into our solar black hole would represent the first continuous source of gravitational radiation ever present in our solar system, creating ripples in space-time that would propagate outward at the speed of light and potentially be detectable by sensitive instruments throughout the galaxy. These waves would carry away energy and angular momentum from infalling matter, causing orbital decay and eventual collapse for any objects that ventured too close to the black hole, but not close enough to be immediately consumed. The stability of planetary orbits throughout our solar system would remain intact for the immediate future. But over longer timescales, the gravitational environment created by our solar black hole would begin to show subtle but important differences from our original solar system. The absence of solar radiation pressure, which normally pushes small particles and dust away from the sun, would allow cosmic dust and debris to accumulate closer to our solar black hole than was ever possible with our active star, potentially creating new structures and patterns in the distribution of matter throughout the inner solar system. All of these gravitational consequences would unfold according to the inexorable mathematics of general relativity, creating a solar system that looks deceptively familiar from a distance, but harbors gravitational secrets and dangers that would make interplanetary travel exponentially more challenging and potentially lethal for any civilization brave enough or foolish enough to attempt navigation in this new cosmic environment. The most immediate and catastrophic consequence of our sun's transformation into a black hole would be the complete and instantaneous cessation of all electromagnetic radiation that has sustained life on Earth for over 3.8 billion years. In the span of just 8 minutes and 20 seconds, the time it takes light to travel from the sun to Earth, our planet would be plunged into a darkness so complete and permanent that it would make the deepest ocean trenches seem brilliantly illuminated by comparison. This wouldn't be like a solar eclipse, where the moon temporarily blocks the sun's light while we can still see the sun's corona dancing around the lunar silhouette. This would be the absolute elimination of our star as a source of energy, replaced by an invisible gravitational monster that consumes light rather than producing it, creating a cosmic void where our life-giving star once blazed with the power of 100 billion hydrogen bombs exploding every second. The last photons of sunlight to leave our dying star would carry with them the final chapter of a 4.6 billion year story of nuclear fusion, electromagnetic radiation, and the delicate energy balance that has made Earth a garden of life in an otherwise hostile cosmos. These photons, born in the crushing depths of the sun's core through the fusion of hydrogen nuclei, would have already begun their epic journey through the sun's radiative zone, bouncing around for thousands of years before finally escaping into space. Now, as they race through the vacuum at 299,792,458 meters per second, they represent the last gift our sun would ever give to the worlds that have depended on its warmth for eons. When these final rays of sunlight wash over Earth's surface, they would illuminate our planet one last time before eternal darkness descends, marking the end of photosynthesis, the end of solar heating, and the beginning of the most rapid climate collapse in planetary history. The physics of our planet's energy budget would undergo a transformation so dramatic that it would dwarf every climate change event in geological history combined. Earth currently receives approximately 1,361 watts of solar energy per square meter at the top of our atmosphere, a value so fundamental to our planet's climate system that scientists have named it the solar constant. This energy input drives virtually every weather pattern, ocean current, and atmospheric circulation system on our planet. From the trade winds that sailors have relied on for centuries to the jet streams that guide commercial aviation routes around the globe. Within moments of our solar black hole's formation, this energy input would drop to exactly zero, not gradually over years or decades, as in natural climate variations, but instantaneously, creating an energy deficit that no natural process could possibly compensate for. The immediate effect on Earth's surface temperature would be both rapid and relentless, following the Stefan Boltzmann law of blackbody radiation with mathematical precision. Without the sun's energy input to balance the energy our planet radiates away into space, Earth would begin cooling at a rate determined entirely by how efficiently it could shed its stored thermal energy. The average global temperature, currently about 15 degrees Celsius, would begin dropping immediately as our planet started radiating away its accumulated heat energy without any solar input to replenish it. The rate of this cooling would be most dramatic in the first hours and days, when the temperature differential between Earth and the cosmic background, temperature of space, would be greatest, creating the maximum possible rate of heat loss according to the laws of thermodynamics. Within the first 24 hours after the last sunlight faded from our skies, Earth's average surface temperature would drop by approximately 1.2 degrees Celsius, a temperature change that might seem modest but would represent the beginning of an exponential cooling curve that would ultimately prove fatal to virtually all life on our planet. The cooling wouldn't be uniform across Earth's surface. Areas that had been experiencing daytime when the transformation occurred would retain slightly more thermal energy initially, while regions that had been in darkness would cool even more rapidly. The oceans, with their enormous thermal mass and capacity to store heat energy, would initially moderate this temperature decline, acting as vast thermal reservoirs that could temporarily slow the planet's cooling by releasing stored heat energy accumulated over decades of solar warming. The absence of solar heating would trigger a cascade of atmospheric changes that would fundamentally alter Earth's weather patterns within hours of the transformation. The differential heating between Earth's equatorial and polar regions, which currently drives the circulation patterns that distribute heat around our planet, would begin to diminish rapidly as both regions cooled toward the same final equilibrium temperature. The massive convection cells that create our trade winds, westerlies, and polar easterlies would begin to weaken and eventually collapse entirely as the temperature gradients that drive them disappeared. The jet streams, those high-altitude rivers of fast-moving air that currently circle our planet and influence weather patterns across entire continents, would slow down and eventually stall as the temperature differences between tropical and polar air masses equalized in the universal cooling. Photosynthesis, the fundamental biological process that converts sunlight into chemical energy and forms the base of virtually every food chain on Earth, would cease immediately and completely. The 150 billion tons of carbon dioxide that plants currently convert into oxygen and organic compounds each year through photosynthesis would remain in our atmosphere, while the production of new oxygen would stop entirely. Plants, from towering redwood trees to microscopic phytoplankton in the oceans, would begin dying within days as their stored energy reserves became exhausted and their cellular machinery ground to a halt without the solar energy needed to power their metabolic processes. The oxygen levels in our atmosphere, currently maintained at about 21% through the constant activity of photosynthetic organisms, would begin a slow but inexorable decline as oxygen continued to be consumed by respiration, combustion, and oxidation processes, while no new oxygen was being produced. The psychological and social effects of permanent darkness would be as devastating as the physical changes, creating a global crisis that would challenge every aspect of human civilization. The human circadian rhythm, evolved over millions of years to synchronize with the daily cycle of sunlight and darkness, would be completely disrupted, leading to widespread sleep disorders, depression, and cognitive impairment across the entire global population. The absence of natural light would trigger seasonal affective disorder on a planetary scale, as the biochemical processes in human brains that depend on sunlight exposure for the regulation of serotonin and melatonin production would be thrown into chaos. Agricultural systems that currently feed 7.8 billion people would collapse within weeks as crops died in their fields and livestock began dying from exposure to the rapidly cooling temperatures. The Earth's hydrological cycle, powered entirely by solar energy that evaporates water from oceans, rivers, and lakes and lifts it into the atmosphere to fall again as precipitation, would begin shutting down within days of our solar transformation. Without solar heating to drive evaporation, the formation of new clouds would slow dramatically and eventually stop entirely. The water vapor currently suspended in our atmosphere would begin condensing and precipitating out, initially as rain in the warmer equatorial regions, but increasingly as snow, and eventually as frozen precipitation that would never melt again. The massive weather systems that currently bring life-giving rain to agricultural regions around the world would fade away, replaced by an eerie calm as atmospheric circulation patterns collapsed and the skies cleared for the final time. Perhaps most ironically, the absence of our sun would create the most spectacular night sky in human history, at least temporarily, while our atmosphere remained transparent and our technology continued functioning. With no solar light to create atmospheric scattering and obscure faint objects, the stars, planets, and galaxies visible from Earth would shine with a clarity and brilliance never before seen by human eyes. The Milky Way galaxy would stretch across the sky in unprecedented detail, while distant galaxies and nebulae, normally visible only through powerful telescopes, would become apparent to the naked eye. This cosmic light show would serve as a bittersweet reminder of the vast universe surrounding our cooling planet, a universe full of other stars whose light would continue shining across the cosmos long after Earth had frozen into a barren ice ball, orbiting an invisible gravitational monster. The infrared radiation that Earth emits into space would continue unabated, following the inviolable laws of thermodynamics as our planet radiated away its thermal energy at a rate proportional to the fourth power of its temperature. This heat loss would be invisible to human eyes, but detectable by thermal imaging systems, showing our planet as a glowing ember slowly fading in the cosmic darkness. The rate of cooling would gradually slow as Earth's temperature dropped and the differential between our planet and the cosmic background radiation decreased. But the cooling would never stop completely until thermal equilibrium was reached at the incredibly cold temperature of deep space. Minus 270 degrees Celsius, just 3 degrees above absolute zero. Human technology and infrastructure would begin failing within hours as the electrical power grids that depend on solar panels for an increasing percentage of global electricity production went offline permanently, while power plants that burned fossil fuels would face rapidly increasing demand for heating, just as transportation systems began struggling with the logistics of moving fuel and supplies in the chaos of permanent darkness and rapidly deteriorating weather conditions. As Earth plunged into perpetual darkness and the relentless cooling began, our planet's atmosphere would undergo one of the most dramatic transformations in the history of planetary science, a process so extraordinary and terrifying that it would redefine our understanding of what it means for a world to be habitable. The atmospheric collapse wouldn't happen all at once. Instead, it would unfold in distinct phases, each more catastrophic than the last, as the fundamental physics governing gas behavior in extreme cold conditions played out on a planetary scale. This wouldn't be a gentle transition or a gradual climate shift that ecosystems might potentially adapt to over thousands of years. This would be an atmospheric apocalypse unfolding over weeks and months, transforming our life-sustaining envelope of gases into a frozen shell of crystallized air, literally falling from the sky. The first component of Earth's atmosphere to begin its dramatic transformation would be water vapor, that crucial greenhouse gas that currently helps regulate our planet's temperature and makes life as we know it possible. Water vapor typically accounts for about 1 to 4% of our atmosphere by volume, varying dramatically with location, season, and weather conditions. But its influence on Earth's climate system is far greater than this relatively small percentage might suggest. As global temperatures plummeted in the days following our solar transformation, the atmosphere's capacity to hold water vapor would decrease exponentially according to the Clausius-Clapeyron relation, a fundamental principle of thermodynamics that describes how the saturation vapor pressure of water decreases dramatically as temperature drops. For every 10 degrees Celsius drop in temperature, the atmosphere's ability to hold water vapor would decrease by approximately 50%. creating a cascading effect that would accelerate the removal of this critical atmospheric component. Within the first week of cooling, as Earth's average temperature dropped below freezing, virtually all water vapor in the atmosphere would begin condensing and precipitating out as snow, ice crystals, and frost. This wouldn't be ordinary snowfall that melts in the spring. This would be the permanent removal of water from our atmospheric system, creating snowfalls and ice storms of unprecedented intensity and duration. The massive cloud systems that currently circle our planet would release their moisture in final catastrophic precipitation events before dissipating forever, leaving behind crystalline deposits of frozen water that would accumulate in layers across Earth's surface like geological strata, marking the death of our climate system. The latent heat released during this phase change would temporarily slow Earth's cooling, but only briefly, as this represents just a tiny fraction of the thermal energy our planet would be radiating away into the cosmic void every second. As temperatures continued their relentless decline, reaching -40 degrees Celsius within the first month, carbon dioxide would begin its own spectacular phase transition from gas to solid, bypassing the liquid phase entirely in a process called sublimation occurring in reverse. Carbon dioxide, that crucial component of our atmospheric system that currently comprises about 420 parts per million of our atmosphere and plays such a vital role in plant photosynthesis and global climate regulation, would begin forming dry ice crystals in the atmosphere before falling to Earth's surface as carbon dioxide snow. This process would be unlike anything ever witnessed in Earth's geological history, creating blizzards of dry ice that would accumulate in massive deposits across the planet's surface, gradually reducing the atmospheric pressure and fundamentally altering the chemical composition of the air itself. The physics governing this atmospheric collapse would follow the ideal gas law with terrifying precision, as the relationship between temperature, pressure, and volume played out on a planetary scale. As the temperature of our atmospheric gases decreased, their volume would contract proportionally. But since Earth's surface area remained constant, this volume reduction would manifest as a decrease in atmospheric pressure and height. The troposphere, that lowest layer of our atmosphere where all weather occurs, and where most atmospheric mass is concentrated, would begin to contract vertically, bringing the higher, colder layers of the atmosphere closer to Earth's surface and accelerating the cooling process through increased radiative heat loss. The nitrogen that comprises 78% of our atmosphere would prove more resistant to this collapse than water vapor and carbon dioxide. But even this most stable component of Earth's atmospheric system would eventually succumb to the extreme cold. Nitrogen has a much lower freezing point than water or carbon dioxide, remaining gaseous until temperatures reach -196 degrees Celsius. But as Earth continued cooling over the months following our solar transformation, even this hardy atmospheric component would begin its own phase transition. The process would be gradual at first, with nitrogen beginning to condense into liquid droplets in the coldest regions of the planet. The polar areas that would cool fastest due to their reduced thermal mass and increased surface area for heat radiation. The oxygen that makes up 21% of our atmosphere and is absolutely essential for virtually all complex life on Earth would follow a similar timeline to nitrogen, remaining gaseous until temperatures drop to -183 degrees Celsius. But long before these components began freezing out of the atmosphere, their behavior would change dramatically due to the reduced atmospheric pressure and altered atmospheric circulation patterns. The partial pressure of oxygen would decrease not just due to cooling, but also due to the removal of other atmospheric components, making breathing increasingly difficult for any surviving air-breathing organisms, even before the oxygen itself began to freeze. Within 3 months of our solar black hole transformation, Earth's atmospheric pressure would have dropped to less than 50% of its original value, as water vapor and carbon dioxide were permanently removed from the atmospheric system. This pressure reduction would have devastating effects on any remaining liquid water on Earth's surface, causing it to boil at lower temperatures, even as the overall environmental temperature continued dropping. The combination of reduced pressure and freezing temperatures would create a situation where water could neither exist as a stable liquid nor remain as a gas, forcing it into solid form and contributing to the growing accumulation of ice covering our planet's surface. The atmospheric circulation patterns that currently distribute heat, moisture, and atmospheric gases around our planet would undergo complete collapse as the temperature gradients that drive these systems disappeared. The Hadley cells, Ferrel cells, and polar cells that currently create our trade winds, westerlies, and weather patterns would fade away entirely, leaving behind an eerily still atmosphere with virtually no horizontal air movement. Without these circulation systems to mix and distribute atmospheric gases, different regions of Earth would experience varying rates of atmospheric collapse, with some areas potentially retaining thin envelopes of the most cold-resistant gases, while others became completely airless. The chemical reactions that normally occur in our atmosphere would also cease or change dramatically as temperatures dropped below the activation energies required for most atmospheric chemistry. The ozone layer that currently protects Earth's surface from harmful ultraviolet radiation would become irrelevant, not because it was being destroyed, but because there would be no more ultraviolet radiation from our sun to block. The complex photochemical reactions that maintain the delicate balance of atmospheric chemistry would stop completely, freezing our atmospheric composition at whatever state it happened to be in when temperatures dropped below the thresholds for chemical activity. Perhaps most remarkably, the atmospheric collapse would create layers of different frozen gases across Earth's surface, essentially turning our planet into a geological record of atmospheric composition frozen in time. The heaviest gases would settle closest to the surface, while lighter gases would form upper layers, creating a stratified deposit of Earth's former atmosphere, preserved as a fossil record of what our planet's air once contained. These layers would be visible to any hypothetical future observers as distinct bands of different colored ices, each representing a different component of the atmospheric system that once supported a thriving biosphere. The rate of atmospheric collapse would accelerate as the process continued, creating positive feedback loops that would make the transformation increasingly rapid and irreversible. As atmospheric pressure decreased, the remaining gases would have less thermal mass to resist further cooling, making them more susceptible to phase changes. As atmospheric circulation ceased, local cooling would accelerate because heat could no longer be transported from one region to another, creating cold spots where atmospheric collapse would occur even more rapidly than the global average. The final stages of atmospheric collapse would occur when temperatures reach the freezing points of nitrogen and oxygen, transforming even these most persistent atmospheric components into frozen deposits on Earth's surface. At this point, perhaps 6 to 12 months after our solar transformation, Earth would possess only the thinnest possible atmosphere consisting of whatever trace gases had the lowest freezing points, perhaps some noble gases, like helium, that would remain gaseous until temperatures approached absolute zero. The atmospheric pressure would be so low that it would be comparable to the near vacuum conditions found in the upper reaches of our current atmosphere, making Earth's surface environment essentially equivalent to the airless surface of the Moon. The silence that would accompany this atmospheric collapse would be one of the most psychologically devastating aspects of Earth's transformation. Sound waves require an atmospheric medium to travel through, and as our atmosphere thinned and eventually disappeared, the world would become increasingly quiet until even the loudest sounds became muffled whispers, and eventually no sound at all could propagate across Earth's surface. The howling winds, crashing waves, and rustling leaves that have provided the soundtrack to life on Earth for billions of years would fade away, replaced by the absolute silence of an airless world where the only sounds that could be heard would be those conducted through solid materials like the ground beneath one's feet. This atmospheric collapse would represent not just the end of weather as we know it, but the complete transformation of Earth from a dynamic, living world into a cold, airless ball of rock and ice orbiting an invisible gravitational monster. A planetary corpse preserving the frozen remains of what was once the most vibrant and life-sustaining atmosphere in the known universe. The transformation of Earth's oceans from vibrant, life-sustaining bodies of liquid water into vast, frozen wastelands would represent one of the most spectacular and terrifying geological events in planetary history. A process so fundamentally dramatic that it would dwarf every ice age, volcanic eruption, and mass extinction event that Earth has ever experienced combined. Our planet's oceans currently contain approximately 1.386 billion cubic kilometers of water, a mass so enormous that it represents about 0.023% of Earth's total mass and covers 71% of our planet's surface to an average depth of 3.68 kilometers. This immense volume of liquid water serves as Earth's primary thermal reservoir, storing and redistributing solar energy on a scale that makes our oceans the primary drivers of global climate patterns, weather systems, and the delicate temperature balance that has allowed life to flourish for over 3.8 billion years. The physics governing the freezing of Earth's oceans would unfold according to the fundamental principles of thermodynamics, but on a scale and timeline unlike anything in recorded geological history. Water has an extraordinarily high specific heat capacity, meaning it can absorb and store tremendous amounts of thermal energy before its temperature changes significantly. Each gram of liquid water must lose 4.18 joules of energy for its temperature to drop by 1 degree Celsius, and then an additional 334 joules per gram must be removed during the actual freezing process as water undergoes the phase change from liquid to solid ice. When we multiply these energy requirements by the total mass of Earth's oceans, approximately 1.4 times 10 to the 21st kilograms, we arrive at energy numbers so large they challenge human comprehension, representing thermal energy equivalent to the total energy output of our sun for several hours. In the first weeks following our solar transformation, the ocean surfaces would begin their freezing process as atmospheric temperatures plummeted below the freezing point of seawater, which occurs at approximately minus 1.8 degrees Celsius due to the dissolved salts that lower water's freezing point. The initial formation of sea ice would follow patterns similar to what we currently observe in polar regions, but accelerated and intensified beyond anything in Earth's climatic history. Unlike normal sea ice formation, which occurs seasonally and melts during warmer periods, this ice formation would be permanent and relentless, growing thicker and more extensive with each passing day as heat continued radiating away from our planet without any solar energy input to replenish the thermal reservoir. The process would begin at the ocean surfaces, where water directly exposed to the increasingly frigid atmosphere would lose heat through evaporation, radiation, and conduction. The first ice crystals would form as frazzle ice, tiny, needle-like crystals suspended in the water column, before consolidating into thin sheets of sea ice that would rapidly thicken as more water froze beneath them. The formation of this initial ice layer would actually accelerate the cooling process through a positive feedback mechanism, as ice reflects much more solar radiation than liquid water. And in our scenario, the highly reflective ice surface would prevent any residual thermal energy from being retained by the ocean system. As the surface ice thickened from centimeters to meters and then to tens of meters, the thermal dynamics of the ocean system would undergo fundamental changes that would seal the fate of these massive water bodies. Ice is an excellent insulator compared to liquid water, meaning that the thickening ice layer would begin to insulate the deeper ocean waters from the frigid atmospheric temperatures above. This insulation effect might initially seem like it would slow the freezing process, but the mathematics of heat transfer would ultimately work against the liquid water beneath the ice. With no solar energy input to warm the ocean surfaces and break up the ice, and with the atmosphere continuing to cool toward the background temperature of space, the thermal gradient between the deep ocean waters and the surface would create an inexorable heat flow that would gradually freeze the oceans from the top down. The salinity of seawater would create complex dynamics during this freezing process that would fundamentally alter the chemical composition of both the ice and the remaining liquid water. As seawater freezes, pure water crystallizes into ice, while the dissolved salts are excluded from the ice crystal structure, concentrating the brine that remains liquid. This process, known as brine rejection, would create increasingly salty water beneath the growing ice layers, water so concentrated with dissolved minerals that its freezing point would be pushed lower and lower, potentially allowing liquid brine to persist in pockets and channels within the ice, even as temperatures dropped well below the normal freezing point of seawater. The freezing process would not be uniform across all of Earth's oceans, creating a complex timeline of transformation that would vary dramatically based on depth, salinity, and geographic location. The shallow seas and coastal areas would freeze completely within the first few months, as their reduced thermal mass would make them more susceptible to the atmospheric cooling. The vast deep ocean basins, the Pacific, Atlantic, and Indian Oceans, would take much longer to freeze completely due to their enormous thermal reservoirs. But even these massive bodies of water would eventually succumb to the relentless cooling as heat continued flowing upward through the thickening ice layers and radiating away into space. Perhaps most remarkably, the pressure at the bottom of the deepest ocean trenches would create conditions where liquid water could theoretically persist even at temperatures well below its normal freezing point. At the bottom of the Mariana Trench, where pressures exceed 1,000 times atmospheric pressure, water's freezing point would be depressed to approximately minus 7.5 degrees Celsius. This means that the very deepest parts of Earth's oceans might remain liquid longer than any other surface water, creating isolated pockets of liquid water in the abyssal depths that would represent the last remnants of Earth's once vibrant hydrological system. The biological implications of ocean freezing would be catastrophic beyond imagination, as these water bodies currently support the vast majority of life on Earth by mass and biomass. Marine ecosystems, from microscopic phytoplankton that produce over 50% of Earth's oxygen to massive whales that migrate across entire ocean basins, would face immediate extinction as their liquid habitat transformed into solid ice. The phytoplankton that form the base of oceanic food webs would die within days of the ocean surface freezing, not just from the cold temperatures, but from the elimination of sunlight needed for photosynthesis. As these organisms died and decomposed, they would consume dissolved oxygen in the water, creating anaerobic conditions that would accelerate the death of other marine organisms in a cascading ecological collapse. The formation of ice layers kilometers thick across Earth's ocean basins would fundamentally alter our planet's geology and surface topography in ways that would be visible from space and detectable by seismic monitoring systems around the world. The expansion of water as it freezes, approximately 9% increase in volume, would create enormous pressures on the ocean floors and continental margins, potentially triggering underwater landslides, seismic activity, and changes in the stress patterns affecting tectonic plate boundaries. The weight of ice accumulating on continental shelves could literally push down on the underlying rock formations, creating measurable changes in Earth's gravitational field and rotational characteristics. The complete freezing of Earth's oceans would also eliminate the thermohaline circulation system, the global network of ocean currents, driven by differences in water temperature and salinity that currently helps distribute heat around our planet. This circulation system, sometimes called the global conveyor belt, moves warm water from equatorial regions toward the poles, while bringing cold water back toward the equator, moderating temperature extremes and influencing weather patterns across entire continents. With the oceans frozen solid, this heat distribution system would cease permanently, eliminating one of Earth's primary climate regulation mechanisms and ensuring that regional temperature variations would be determined entirely by local heat retention and loss rather than global heat redistribution. The ice that formed from Earth's frozen oceans would not be uniform in composition or appearance, but would instead create a complex geological record of the freezing process itself. Different layers of ice would contain different concentrations of dissolved gases, minerals, and organic matter, creating visible stratification that would tell the story of how Earth's oceans died. The deepest layers of ice, formed from the last liquid water to freeze, would contain the highest concentrations of dissolved salts and minerals, creating dense, cloudy ice that would be distinctly different from the clearer ice formed from surface waters that had lower mineral content. Perhaps most poignantly, the frozen oceans would preserve within their ice layers the remains of Earth's marine biosphere, creating a three-dimensional fossil record of oceanic life frozen in time. Microscopic organisms, fish, marine mammals, and all the countless life forms that called Earth's oceans home would be preserved within the ice layers, creating what could be considered the largest and most complete paleontological collection in the history of our planet. Future observers, if any existed, would be able to study these preserved remains to understand exactly what Earth's oceanic ecosystems looked like during their final moments. The transformation of Earth's oceans from liquid to solid would represent far more than just a physical change of state. It would mark the end of the hydrological cycle that has shaped our planet's climate, weather, and geography for billions of years. The evaporation, cloud formation, precipitation, and runoff that currently move water between oceans, atmosphere, and land would cease permanently, leaving Earth with a static water inventory frozen in place. The tidal forces that currently move trillions of gallons of seawater twice daily, creating coastal ecosystems and influencing marine life cycles, would become meaningless as our planet's water transformed from a dynamic, flowing system into a solid, immobile mass of ice that would remain frozen for millions of years, until long after any memory of Earth's living oceans had faded into cosmic history. The complete cessation of solar energy would trigger the most rapid and comprehensive mass extinction event in Earth's 4.5 billion year history, a biological apocalypse so thorough and devastating that it would make the Permian-Triassic extinction, which eliminated 96% of marine species and 70% of terrestrial vertebrates, seem like a minor ecological hiccup by comparison. Every single organism on Earth, from the smallest bacteria to the largest whales, from ancient redwood trees that have stood for millennia to microscopic tardigrades renowned for their incredible resilience, would face an immediate and existential crisis as the fundamental energy source that powers virtually all life on our planet disappeared forever. This wouldn't be a gradual die-off over thousands or millions of years that might allow for evolutionary adaptation. This would be biological Armageddon unfolding over weeks and months as the intricate web of life that has taken billions of years to evolve would unravel with terrifying speed. The primary producers that form the foundation of virtually every ecosystem on Earth would be the first casualties in this biological catastrophe, and their death would trigger cascading effects that would doom every other form of life that depends on them for survival. Plants, algae, and photosynthetic bacteria that currently convert approximately 130 billion tons of carbon dioxide into organic compounds each year, through the miracle of photosynthesis, would cease this vital process the moment the last photons of sunlight faded from Earth's atmosphere. Without solar energy to power the light-dependent reactions of photosynthesis, these organisms would be unable to produce the glucose and other organic molecules that serve as both building blocks for cellular growth and fuel for cellular respiration. Within days, as their stored energy reserves became depleted, the chloroplasts that give plants their green color would begin breaking down, and the cellular machinery that has powered life on Earth for over 3 billion years would grind to a halt. The death of photosynthetic organisms would have immediate and catastrophic effects on atmospheric oxygen levels, creating a secondary crisis that would accelerate the extinction process for all aerobic life forms. Earth's atmosphere currently contains about 21% oxygen, a concentration that is maintained through the constant activity of photosynthetic organisms that release oxygen as a byproduct of converting carbon dioxide and water into organic compounds. With photosynthesis completely halted, no new oxygen would be produced, while existing oxygen would continue being consumed by respiration, combustion, and chemical oxidation processes occurring throughout the biosphere. The oxygen concentration in our atmosphere would begin declining immediately, creating hypoxic conditions that would make survival increasingly difficult for all oxygen-breathing organisms, from insects and birds to fish and mammals. Plants would face a particularly cruel fate in this dying world, as they would be among the organisms best equipped to survive the initial temperature drop, but would be completely unable to obtain the energy they need to maintain their cellular functions. Trees that have survived ice ages, droughts, floods, and centuries of environmental change would find themselves in the impossible situation of having adequate water and carbon dioxide available, but lacking the solar energy needed to convert these raw materials into usable fuel. The largest trees, with their massive thermal mass and extensive energy reserves stored in their wood and root systems, might survive for several weeks or even months, slowly consuming their stored carbohydrates while their photosynthetic machinery remained dormant. But even these botanical giants would eventually exhaust their energy reserves and succumb to cellular death as their metabolic processes slowed and stopped in the increasingly frigid environment. Herbivorous animals would face a double catastrophe as both their food sources and their thermal environment became hostile to survival. Large herbivores, like elephants, cattle, and deer, which require enormous quantities of plant matter to sustain their metabolic needs, would find their food supplies dying within days of the solar transformation. These animals might initially attempt to consume the dead and dying vegetation, but without the ongoing production of new plant growth, the available biomass would be quickly exhausted. The largest herbivores, with their high metabolic demands and need for vast quantities of food, would be among the first animals to die from starvation, their massive bodies becoming unable to generate sufficient heat to survive in the rapidly cooling environment, even if food were somehow available. Carnivorous animals might have a slightly longer survival timeline, as the death of herbivores would initially provide abundant carrion for scavenging, but their fate would ultimately be just as sealed as that of their prey. Predators like lions, wolves, and eagles would find themselves in the paradoxical situation of having more food available than ever before as herbivore populations collapsed. But this abundance would be temporary and ultimately meaningless as the entire food web crumbled beneath them. As temperatures continued dropping, even the most efficient predators would find themselves unable to obtain sufficient calories to maintain their body temperature, and the preservation of carrion in the freezing conditions would create its own challenges as frozen meat became increasingly difficult to consume and digest. Marine ecosystems would face their own unique version of this biological apocalypse, with the additional complication of habitat destruction as the oceans themselves transformed from liquid to solid. Marine phytoplankton, which currently produce over 50% of Earth's oxygen and form the base of oceanic food webs, would die within days of losing sunlight, creating a marine dead zone that would propagate upward through every level of oceanic life. Fish, marine mammals, and other sea creatures would face the impossible challenge of finding food in ecosystems where primary productivity had ceased, while simultaneously dealing with their liquid habitat freezing around them. Deep-sea creatures living near hydrothermal vents might have the longest survival potential in marine environments, as these organisms have evolved to derive energy from chemosynthesis rather than photosynthesis. But even these hardy survivors would eventually succumb as the oceans froze and disrupted the geological processes that power their unique ecosystems. Humans, despite our technological advantages and ability to create artificial environments, would face perhaps the most complex survival challenge of any species, as our civilization's dependence on complex infrastructure and global supply chains would become a critical vulnerability in this rapidly changing world. The immediate challenges would be obvious: heating, food production, and maintaining electrical power as solar panels became useless and demand for energy skyrocketed. But the secondary effects would be equally devastating as transportation systems failed in the extreme cold, communication networks went down, and the social structures that hold human civilization together began breaking down under the stress of a global catastrophe beyond anything in human experience. The timeline of human survival would depend heavily on geographic location and access to resources, with some populations potentially surviving longer than others based on their ability to access stored food, fuel, and shelter. People living in regions with abundant coal, natural gas, or nuclear power plants might maintain heating and electricity for extended periods, while those in areas dependent on renewable energy or imported fuel would face immediate crises. Underground facilities, subway systems, and deep basements would become crucial survival shelters as surface temperatures plummeted. But even these protected environments would ultimately become uninhabitable as heating systems failed and food supplies were exhausted. Perhaps most remarkably, some of Earth's most primitive and seemingly fragile organisms might prove to be among the longest survivors in this frozen world. Extremophile bacteria that currently thrive in environments with extreme temperatures, pressure, or chemical conditions might continue surviving long after more complex organisms had perished. These microscopic life forms, some of which can remain dormant for thousands of years and survive in conditions that would instantly kill more complex organisms, represent the most likely candidates for long-term survival in Earth's transformed environment. Tardigrades, those nearly indestructible microscopic animals that can survive in the vacuum of space, extreme radiation, and temperatures approaching absolute zero, might continue existing in cryptobiotic states long after the last human had died. The preservation of life in this dying world would become a race against time and thermodynamics, as any organism that could find ways to reduce its metabolic rate and conserve energy would have survival advantages over those with higher energy requirements. Some small mammals might attempt to enter extended hibernation states, dramatically slowing their metabolism and reducing their energy needs. But even hibernation requires some energy input to maintain basic cellular functions. And without any primary productivity to support food webs, even the most efficient hibernators would eventually exhaust their fat reserves and face starvation. The final phases of life's extinction on Earth would likely occur in the most protected and energy-rich environments. Perhaps in geothermal areas where underground heat sources could provide temporary warmth, or in human-constructed facilities where stored energy could maintain artificial environments for extended periods. But these would be temporary refuges at best, as the fundamental problem would remain unsolvable. Without solar energy to power photosynthesis and drive primary productivity, there would be no renewable source of energy to sustain biological systems over the long term. The last living organisms on Earth would likely be anaerobic bacteria living in deep underground environments where geothermal energy could provide the chemical energy needed for their metabolism, surviving in conditions similar to those where life may have first emerged billions of years ago. These primitive survivors would inherit a world that bore no resemblance to the vibrant biosphere that had flourished under our life-giving sun, representing the final chapter in the story of life on Earth, as they too would eventually succumb when even the planet's internal heat sources could no longer sustain biological processes in the cosmic cold that would define Earth's new reality. The most terrifying and mind-bending consequence of our solar black hole would not be its ability to consume light or its role in Earth's atmospheric collapse, but rather the incredible tidal forces that would stretch, twist, and ultimately tear apart any object unfortunate enough to venture too close to this gravitational monster. These forces represent one of the most alien and counterintuitive aspects of black hole physics, demonstrating how extreme gravity doesn't just pull objects inward, it literally reshapes the very geometry of space and time in ways that would fundamentally violate everything we understand about the structural integrity of matter itself. The term spaghettification might sound almost comical, but the physical reality it describes is perhaps the most horrifying fate that physics can impose on any object, living or otherwise, as the very atoms that comprise matter are stretched beyond their ability to maintain the electromagnetic bonds that give substances their form and identity. To understand why tidal forces become so incredibly dangerous near our solar black hole, we must first grasp the fundamental principle that gravity is not actually a uniform force field, but rather a gradient that becomes steeper and steeper as distance to the gravitational source decreases. In our everyday experience on Earth's surface, this gradient is so gentle that we never notice it. The difference in gravitational pull between your head and your feet is utterly negligible, creating no measurable stress on your body. But near a black hole, where the gravitational field strength increases dramatically, over very short distances, this gradient becomes steep enough to create differential forces that can overcome the strongest materials known to science. The mathematical description of this effect involves calculating the second derivative of the gravitational potential, which represents how rapidly the force changes with position, and near a black hole, this rate of change becomes astronomical. For our solar black hole, with its event horizon located just 3 kilometers from the center, the tidal forces would become dangerous at distances that seem surprisingly far from the black hole itself. At a distance of just 1,000 kilometers from the event horizon, still more than 300 times farther from the black hole's center than the point of no return, the tidal acceleration across a human-sized object would already exceed the tensile strength of biological tissue. This means that a human body at this distance would experience gravitational forces on their feet that are measurably stronger than the forces on their head, creating a stretching effect that would gradually overcome the structural integrity of bones, muscles, and organs. The person would literally be pulled apart by the differential gravitational forces, starting with the weakest tissues and gradually progressing until even the strongest bones could no longer resist the inexorable stretching. The physics underlying spaghettification involves the fundamental relationship between gravitational acceleration and distance, described by Newton's law of universal gravitation and Einstein's more precise general relativistic corrections. Near our solar black hole, the gravitational acceleration would increase as the square of decreasing distance, meaning that moving just slightly closer to the black hole would result in dramatically stronger tidal forces. An object that experiences manageable tidal stress at one distance might find itself literally torn apart just a few kilometers closer to the black hole, creating invisible boundaries in space where the transition from structural integrity to complete destruction occurs over surprisingly short distances. The process of spaghettification would unfold in distinct phases, each more terrifying than the last, as different materials and structures succumb to the overwhelming tidal forces at different distances from our gravitational monster. Biological tissues, with their relatively weak tensile strength compared to metals or ceramics, would be among the first to fail, stretching and tearing in ways that would cause immediate death long before the actual structural failure of bones and organs. A human approaching our solar black hole would first experience the sensation of being stretched vertically while being compressed horizontally as the tidal forces work to reshape any extended object into a long, thin configuration aligned with the direction of gravitational pull. But the horror of spaghettification extends far beyond biological tissues to encompass any material object, regardless of its composition or structural strength. Spacecraft constructed from the strongest aerospace alloys would find their hulls stressed beyond the yield strength of their materials as differential gravitational forces pulled different sections of the vehicle with increasing intensity. A spacecraft 100 meters long, approaching within 500 kilometers of our solar black hole's event horizon, would experience tidal forces sufficient to overcome the tensile strength of steel, causing the vehicle to literally stretch and break apart as if it were made of soft clay rather than high-strength metal alloys. The mathematical description of these tidal forces reveals the truly alien nature of extreme gravitational environments, where the familiar rules governing the behavior of solid matter cease to apply. The tidal acceleration experienced by an object of length L at distance r from our black hole follows the relationship a tidal equals 2 gml over r cubed, where g is the gravitational constant and m is the mass of our solar black hole. This cubic relationship with distance means that tidal forces increase incredibly rapidly as objects approach the black hole. Moving half as close to the black hole results in tidal forces that are 8 times stronger, creating a zone around the black hole where the transition from survivable to lethal tidal forces occurs over remarkably short distances. Even more remarkably, the spaghettification process would affect different parts of the same object at different rates, creating internal stresses that would tear apart even the most carefully engineered structures. Consider a hypothetical spacecraft approaching our solar black hole. The sections of the vehicle closest to the black hole would experience stronger gravitational pull than the sections farther away, but they would also be connected to those more distant sections by the structural framework of the spacecraft itself. This creates a situation where the spacecraft is literally trying to tear itself apart from the inside, as different sections experience different accelerations while remaining mechanically connected to each other. The horizontal compression forces that accompany vertical stretching during spaghettification add another layer of complexity to this already nightmarish process. While objects are being stretched along the direction pointing toward our black hole, they are simultaneously being compressed in the perpendicular directions, as the converging nature of gravitational field lines focuses matter inward. This means that a spherical object approaching our solar black hole would be deformed into an increasingly elongated ellipsoid, growing longer and thinner until the internal stresses exceed the cohesive forces holding the object together, causing it to break apart into smaller pieces that would each continue stretching until they too succumbed to the relentless tidal forces. The atomic and molecular consequences of extreme tidal forces represent perhaps the most fundamental violation of normal matter behavior that physics can impose. At the most extreme distances from our solar black hole, tidal forces would become strong enough to overcome even the electromagnetic forces that bind atoms together in molecules and crystal structures. Individual atoms would find themselves stretched to the point where electrons could no longer maintain stable orbits around atomic nuclei, causing matter to break down at the most fundamental level and creating exotic states of matter that exist nowhere else in the universe except in the immediate vicinity of black holes and neutron stars. The timeline of spaghettification would depend critically on the size, composition, and structural strength of the object experiencing these forces, creating different destruction scenarios for different types of matter. Small objects like human bodies would experience catastrophic structural failure relatively quickly, within seconds or minutes of entering the dangerous tidal zone, while larger, more structurally robust objects might resist the stretching forces for longer periods before ultimately succumbing to the inevitable. A large asteroid, held together by its own gravitational self-attraction, might maintain some semblance of structural integrity closer to our solar black hole than an artificial spacecraft. But even these massive objects would eventually reach their limit and break apart into debris streams spiraling inward toward the event horizon. The observational consequences of spaghettification would create some of the most spectacular and terrifying displays in our solar system. As objects being torn apart by tidal forces would heat up due to the friction and compression involved in their destruction. The mechanical energy involved in stretching and breaking apart matter would be converted into thermal energy, causing the debris to glow with increasing brightness as it spiraled closer to our solar black hole. This heating effect would make the process of spaghettification visible from great distances, creating brilliant streaks of glowing material that would trace the final moments of any object brave enough or unlucky enough to venture too close to our gravitational monster. Perhaps most unsettling of all, the process of spaghettification would continue even after objects had been torn apart into smaller pieces, as each fragment would continue experiencing the same tidal forces that destroyed the original object. The debris created by spaghettification would itself be subjected to further stretching and compression, breaking down into smaller and smaller pieces, until eventually even individual atoms would be disrupted. This creates a cascade effect where matter doesn't just get destroyed once, but continues being destroyed repeatedly at ever smaller scales until it finally crosses the event horizon and disappears from the observable universe forever. The regions around our solar black hole, where these extreme tidal forces operate, would effectively create invisible boundaries in space that would be far more dangerous than the event horizon itself, representing zones where the very concept of structural integrity loses all meaning, and where the familiar properties of matter, strength, cohesion, and form become utterly irrelevant in the face of gravitational forces that reshape reality itself according to the inexorable mathematics of general relativity. The transformation of our sun into a black hole would fundamentally restructure our entire solar system over timescales ranging from immediate gravitational adjustments to cosmic evolutionary changes spanning millions of years, creating a celestial environment so alien to our current solar neighborhood that future astronomers studying this system would struggle to believe it had once harbored a thriving biosphere centered around a life-giving star. While the immediate effects would be catastrophic for Earth and life as we know it, the long-term gravitational dynamics would create a solar system that continues to evolve according to the inexorable laws of physics, but along pathways that would be completely unprecedented in astronomical history. This wouldn't be the gentle, predictable evolution that characterizes normal stellar systems, but rather a dramatic cosmic transformation that would reshape everything from planetary orbits to the distribution of minor bodies throughout our solar neighborhood. The 8 planets of our solar system would initially continue their orbits with remarkable stability, a testament to the fundamental principle that gravitational attraction depends only on mass and distance, not on the physical nature of the massive object creating the gravitational field. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune would all maintain their current orbital periods, eccentricities, and inclinations exactly as they do today, creating the surreal situation where astronomical observations of planetary positions would remain perfectly predictable using the same mathematical models that work for our current sun-centered system. However, this gravitational stability would mask more subtle but profound changes that would gradually accumulate over longer timescales, fundamentally altering the character and evolution of our solar system in ways that would become increasingly apparent over thousands and millions of years. The absence of solar radiation pressure would create the first major deviation from normal solar system evolution, eliminating a force that has shaped the distribution and behavior of small particles throughout our cosmic neighborhood for 4.6 billion years. Solar radiation pressure currently acts like a cosmic wind, constantly pushing dust particles, gas molecules, and small debris away from the inner solar system toward the outer reaches of our planetary neighborhood. This outward pressure is responsible for the distinctive tails of comets, the gradual spiral decay of small asteroids that venture too close to the Sun, and the relatively clean environment of the inner solar system compared to the dust-rich regions beyond the orbit of Mars. With our solar black hole producing no radiation whatsoever, this cleansing mechanism would cease entirely, allowing cosmic dust and debris to accumulate in regions of the inner solar system where it has never been able to establish permanent residence. Over timescales of thousands of years, this accumulation of material would create increasingly dense clouds of dust and small particles throughout the inner solar system, fundamentally changing the environment through which Earth and the other terrestrial planets travel in their orbits. These dust clouds would not pose immediate collision hazards to the planets themselves, but they would create a cosmic fog that would gradually alter the dynamics of smaller objects and potentially affect the long-term stability of asteroid and comet orbits. The gravitational influence of our solar black hole would slowly shepherd this accumulated material into complex orbital patterns, creating ring-like structures and debris fields that would give our transformed solar system an appearance more reminiscent of Saturn's ring system than the relatively clean orbital planes that characterize our current planetary arrangement. The asteroid belt, that collection of rocky debris orbiting between Mars and Jupiter, would undergo perhaps the most dramatic long-term changes of any region in our transformed solar system. Currently maintained in its current configuration by a delicate balance of gravitational influences from Jupiter, Mars, and our Sun, the asteroid belt would find its dynamics fundamentally altered by the concentrated gravitational field of our solar black hole. The absence of radiation pressure would allow smaller asteroids and dust particles to migrate inward toward our black hole, while the unchanged but concentrated gravitational field would create new resonances and orbital relationships that could potentially destabilize some asteroid orbits while stabilizing others in previously impossible configurations. Jupiter, our solar system's gravitational giant, would continue to play its role as a cosmic shepherd, protecting the inner solar system from most long-period comets and asteroids that might otherwise threaten the terrestrial planets. However, the changed dynamics created by our solar black hole would gradually alter the specific mechanisms by which Jupiter provides this protection. The absence of solar wind and radiation pressure would allow some cometary material to penetrate deeper into the inner solar system than ever before, potentially creating new populations of near-Earth objects that would follow orbital patterns never before seen in our planetary neighborhood. Over millions of years, these subtle changes could accumulate to create significantly different impact probabilities for the inner planets, altering the long-term geological evolution of worlds like Mars and the frozen remnant of Earth. The outer planets, Jupiter, Saturn, Uranus, and Neptune, would experience their own unique evolutionary pathways in our transformed solar system, as the absence of solar heating would gradually alter their atmospheric dynamics and internal energy balance. These gas giants currently receive varying amounts of solar energy that influences their atmospheric circulation patterns, storm systems, and seasonal variations. With solar heating eliminated entirely, these planets would depend solely on their internal heat sources for atmospheric dynamics, potentially leading to more stable but less energetic weather patterns and atmospheric circulation. Saturn's magnificent ring system, currently maintained through a complex interplay of gravitational forces and interactions with solar radiation, would find its evolution altered as the absence of radiation pressure changed the behavior of the microscopic ice and rock particles that comprise the rings. The moons of the outer planets would face their own long-term evolutionary challenges as they orbited worlds that were themselves gradually cooling and changing in the permanent darkness of our transformed solar system. Europa, with its subsurface ocean currently maintained by tidal heating from Jupiter's gravitational field, might actually benefit from the elimination of solar thermal variations that currently cause stress cycling in its icy crust. The absence of solar radiation would create more stable thermal conditions on Europa's surface, potentially allowing its subsurface ocean to maintain liquid conditions for longer periods than might be possible in a system where solar heating created thermal stress cycles that could disrupt the delicate balance maintaining liquid water beneath the ice. The Kuiper Belt and Oort cloud, those vast reservoirs of icy objects in the outer reaches of our solar system, would experience the most dramatic long-term changes of any region in our cosmic neighborhood. Currently, these regions occasionally release comets toward the inner solar system when gravitational perturbations from passing stars or galactic tidal forces disturb their pristine orbital configurations. With our solar black hole providing a more concentrated gravitational field than our original sun, the dynamics governing these distant objects would shift in subtle but important ways. Some objects that are currently in stable orbits in these distant regions might find their orbits gradually altered by the changed gravitational environment, potentially leading to increased comet activity over very long timescales as objects that have remained undisturbed for millions of years begin following new orbital pathways. The galactic environment surrounding our solar system would also interact differently with our transformed stellar neighborhood, creating cosmic-scale evolutionary changes that would unfold over millions of years. Our solar system currently moves through the galaxy in an environment where our sun's heliosphere, the bubble of solar wind that surrounds our planetary neighborhood, provides some protection from interstellar radiation and charged particles. With our solar black hole producing no stellar wind, this protective bubble would collapse entirely, allowing interstellar matter and radiation to penetrate much deeper into our solar system than ever before. Over cosmic timescales, this could lead to the gradual accumulation of interstellar dust and gas throughout our planetary neighborhood, fundamentally altering the composition and density of the space environment in which our planets orbit. Perhaps most remarkably, our solar black hole would begin to accumulate matter over very long timescales, gradually growing in mass and size as cosmic dust, interstellar gas, and occasional larger objects fell past the event horizon and disappeared forever into the gravitational monster at our system's center. This accretion process would be extremely slow compared to the dramatic matter consumption seen around active black holes in other astronomical contexts. But over millions of years, even this gradual accumulation would measurably increase the mass of our solar black hole. As the black hole's mass increased, its gravitational influence would strengthen proportionally, gradually altering the orbital dynamics throughout our solar system in ways that would be utterly imperceptible on human timescales, but could become significant over geological time periods. The long-term thermal evolution of our solar system would follow a pathway toward ultimate thermal equilibrium with the cosmic background radiation, creating a final state where all objects in our planetary neighborhood would eventually reach the same incredibly cold temperature of deep space. This cooling process would unfold over timescales so vast that they challenge human comprehension. Millions of years for the smallest objects, potentially billions of years for the largest planets with significant internal heat sources. During this cosmic cooling, our solar system would gradually transition from a collection of warm worlds orbiting a central energy source to a cold, dark arrangement of frozen objects circling an invisible gravitational anchor, representing a fundamental transformation from a dynamic, energy-rich system to a stable, low-energy gravitational collective that would persist essentially unchanged for cosmic ages that dwarf the current age of the universe itself. As we reach the final chapter of our cosmic nightmare scenario, it's crucial to understand that the transformation we've explored, our sun becoming a black hole, represents one of the most impossible events that physics can conceive, violating fundamental laws of stellar evolution that are as ironclad as the speed of light or the conservation of energy. Real black hole formation is a process so dramatically different from our hypothetical scenario that it involves completely different physics, entirely different timescales, and stars that are fundamentally unlike our sun in almost every conceivable way. The actual universe creates black holes through mechanisms so violent and extreme that they dwarf even our terrifying thought experiment, involving stellar explosions that release more energy in seconds than our sun will produce over its entire 10 billion year lifetime, and gravitational collapses so rapid and complete that they represent some of the most extreme physical processes that occur anywhere in the cosmos. The pathway to real black hole formation begins with stars that are at least 20 to 25 times more massive than our sun. Stellar behemoths so enormous and energetically active that they represent fundamentally different categories of astronomical objects than the relatively modest, long-lived star that warms our planet. These massive stars live fast and die young, burning through their nuclear fuel at rates that are thousands of times faster than our sun's leisurely consumption of hydrogen. Where our sun will maintain stable nuclear fusion for approximately 10 billion years, with about 5 billion years already behind us and another 5 billion years ahead, These massive stars exhaust their fuel supplies in just a few million years, racing through stellar evolution at breakneck speed as their enormous gravitational fields create core pressures and temperatures so extreme that nuclear fusion reactions proceed at rates that would tear apart smaller stars. The nuclear physics governing massive stars is far more complex and energetic than the relatively simple hydrogen to helium fusion that powers our Sun, involving a series of increasingly violent fusion reactions that create progressively heavier elements in the stellar core. These massive stars progress through hydrogen burning, helium burning, carbon burning, oxygen burning, and silicon burning in an accelerating cascade of nuclear processes that each operate at higher temperatures and pressures than the last. The final stage, silicon burning, creates iron 56 in the stellar core, and this represents a fundamental dead end in stellar energy production because iron 56 has the highest binding energy per nucleon of any atomic nucleus, meaning that neither fission nor fusion of iron can release additional nuclear energy to support the star against gravitational collapse. When a massive star's core becomes dominated by iron 56, it faces an impossible situation that leads directly to the most violent explosion in the known universe. The core can no longer generate the outward radiation pressure needed to balance the inward pull of gravity, and catastrophic collapse becomes inevitable. This collapse doesn't unfold gradually over years or months. It happens in less than 1 second, as the stellar core, which might be the size of Earth, but contain more mass than our Sun, suddenly finds itself unable to resist gravitational compression. The core temperature rises to over 10 billion degrees Celsius as gravitational potential energy is converted to thermal energy. But even this incredible temperature cannot generate enough pressure to halt the collapse because iron fusion is endothermic rather than exothermic, actually absorbing energy rather than releasing it. The collapse continues until the stellar core reaches nuclear density, approximately 3 times 10 to the 17th kilograms per cubic meter, at which point the strong nuclear force finally provides enough resistance to temporarily halt the gravitational compression. This creates a core bounce that sends a massive shock wave racing outward through the star's outer layers. But in stars massive enough to form black holes, even this incredible explosion is insufficient to halt the gravitational collapse. The shock wave stalls as it encounters the massive outer layers of the stellar envelope, and the core continues contracting beyond nuclear density into realms of physics that challenge our current theoretical understanding. As the stellar core contracts beyond the point where even neutron degeneracy pressure can provide resistance, it crosses the event horizon radius for its mass, creating a black hole in the heart of the dying star, while the outer layers continue their explosive expansion in what astronomers observe as a hypernova, an explosion so energetic that it can briefly outshine an entire galaxy containing billions of stars. The formation of the event horizon marks the point where space-time curvature becomes so extreme that not even light can escape. And from this moment forward, the black hole can only grow as it continues accreting matter from the stellar explosion occurring around it. The mass requirements for black hole formation represent one of the most fundamental differences between our hypothetical scenario and reality. Our Sun, with its mass of 2 times 10 to the 30 kilograms, falls far short of the minimum mass needed for black hole formation. The Tolman-Oppenheimer-Volkoff limit of approximately 2.17 solar masses. This isn't just a minor deficiency that might be overcome with some additional matter. It represents a fundamental categorical difference between stars that can form black holes and those that cannot. Stars below this mass threshold will never form black holes regardless of any external influences or catastrophic events that might befall them. They are destined for entirely different evolutionary pathways that lead to white dwarf formation, planetary nebula creation, or at most, neutron star formation in the case of stars just below the black hole threshold. The observational signatures of real black hole formation are among the most spectacular phenomena in astronomy, creating gamma-ray bursts that can be detected across billions of light years and gravitational wave emissions that ripple through the fabric of space-time itself. When a massive star collapses to form a black hole, the conservation of angular momentum causes the collapsing core to spin faster and faster, potentially reaching rotation rates where the black hole spins hundreds of times per second. This rapid rotation can create powerful jets of material moving at nearly the speed of light, shooting outward from the black hole's poles and creating the most energetic explosions known to occur in the universe. The timescales involved in real black hole formation are as dramatically different from our scenario as the mass requirements, unfolding over microseconds rather than the instantaneous transformation we imagined. The actual core collapse occurs in less than 1 second, but this represents the culmination of nuclear burning phases that have been building toward this moment for millions of years. The silicon burning phase that immediately precedes core collapse might last only days or weeks, while the oxygen burning phase that precedes silicon burning might continue for months or years. This represents stellar evolution compressed into timescales that are still incredibly rapid compared to the billions of years that characterize our sun's leisurely progression through its life cycle. The environments where real black holes form are cosmic violence factories that bear no resemblance to our stable, life-supporting solar neighborhood. The massive stars that create black holes exist in regions of space where stellar densities are high, radiation fields are intense, and gravitational interactions between multiple massive stars create chaotic orbital dynamics that can lead to stellar collisions, mass transfer events, and other catastrophic interactions. These stars often exist as part of binary or multiple star systems where they exchange matter with companion stars, creating accretion disks, X-ray emissions, and other high-energy phenomena that would make the space environment utterly hostile to planetary formation or biological life. The black holes created through real stellar evolution possess characteristics that would be fundamentally different from our hypothetical solar black hole, particularly in terms of their rotation rates and magnetic field configurations. Stellar mass, black holes formed from collapsed massive stars typically possess significant angular momentum inherited from their progenitor stars, causing them to rotate at substantial fractions of their maximum possible rotation rates. This rotation creates ergospheres, frame-dragging effects, and other relativistic phenomena that would be far more extreme than anything our slowly rotating solar black hole would produce. The ultimate fate of stellar mass black holes formed through natural processes is vastly different from the stable, long-lived object we imagined in our solar system scenario. Real black holes continue growing through accretion of surrounding matter, potentially merging with other black holes in spectacular collisions that create gravitational waves detectable across cosmic distances. Over the incredibly long timescales of cosmic evolution, stellar mass black holes can grow to become intermediate mass black holes and potentially contribute to the formation of the supermassive black holes found at the centers of galaxies. Perhaps most remarkably, the study of real black hole formation has revealed that these objects are not the cosmic monsters of science fiction imagination, but rather fundamental components of cosmic evolution that play crucial roles in the formation and evolution of galaxies, the distribution of heavy elements throughout the universe, and the overall structure of space-time on the largest scales. The energy released during black hole formation and the subsequent accretion processes contribute to the heating of intergalactic gas, the regulation of star formation rates in galaxies, and the creation and distribution of the heavy elements that make rocky planets and biological life possible. Our exploration of an impossible scenario has revealed the incredible precision and balance that characterizes our actual solar system, where a star of exactly the right mass, age, and composition has created conditions suitable for the emergence and evolution of life over billions of years. The real universe, with its authentic mechanisms for black hole formation, its genuine stellar evolution processes, and its actual physics governing the behavior of matter and energy, creates a cosmos far more remarkable and precisely tuned for complexity and life than any science fiction scenario could imagine. As we conclude this cosmic journey through impossible physics and terrifying scenarios, remember that our real sun will continue shining steadily for another 5 billion years, gradually growing brighter as it ages, but maintaining the stable nuclear fusion that has supported life on Earth for over 3.8 billion years. The universe's actual mechanisms for creating black holes, while far more violent and extreme than our thought experiment, occur in distant regions of space and involve stars so fundamentally different from our Sun that they represent entirely separate categories of cosmic phenomena. If you've enjoyed this mind-bending exploration of impossible physics and cosmic catastrophes, don't forget to subscribe to the Sleepy Cosmos for more journeys through the fascinating and terrifying possibilities that the universe holds. Like this video if it kept you captivated, and let me know in the comments what other cosmic scenarios you'd like us to explore together. Sweet dreams! And remember, our real universe is far more amazing than any nightmare scenario we could imagine.